Temperature and thermometers. In everyday language, many of us use the term temperature and heat interchangeably. But in physics, these terms have very different meanings. Think about this. When you touch a piece of metal and a piece of wood, both resting in front of you, which feels warmer? When do you feel warmer? When the air around you is 90 degrees Fahrenheit and dry, or when it's 90 degrees Fahrenheit and very humid? In both cases, the temperatures of what you're feeling is the same. Then why are you feeling a difference? In this unit, we'll learn about temperature, heat, and the laws of thermodynamics that relate heat, mechanical work, and other forms of energy. So, what is temperature? Well, here's some definitions. A measure of the warmth or coldness of an object or substance with reference to some standard value. Any of various standardized numerical measures of this ability, such as Kelvin, Fahrenheit, or Celsius scales. A measure of the ability of a substance, or more generally of any physical system, to transfer heat energy to another physical system. And finally, a measure of the average kinetic energy of the particles in a sample of matter expressed in terms of units or degrees designated on a standard scale. We'll consider each of these as we proceed through this unit. Well, how can we measure temperature of a substance? Well, first of all, we need a measuring device. We call that a thermometer. The thermometer changes visibly, and it's calibrated to a scale. Thermometers relate the change in a physical property of a substance to temperature. For example, the change of volume of a gas or liquid, or the change in length of a metal strip or wire. We'll look at these changes next. It can also be a measurement of light or infrared radiation emitted by an object, and we'll look at that too later. Then we need to bring our thermometer in contact with the substance. When the thermometer has settled on a value, we say that the thermometer and the substance are in thermal equilibrium. We'll also explore thermal equilibrium in a subsequent section. Here we have some example thermometers. The common bulb-type thermometer with its reservoir at its base and a thin column into which the liquid expands as temperature increases. The bimetallic strip-type thermometer, which is the common dial-type thermometer you might see, for example, in old-fashioned thermostats. In this one, the two metals making up a spring expand at different rates, causing the spring to wind tighter or loosen, thereby moving a pointer. And finally, we have a gas thermometer. As the gas increases in temperature, its pressure increases. This registers on a manometer or pressure gauge, and that in turn can be calibrated to temperature. The thermometers that we've just described undergo a physical change, a contraction or expansion with temperature. But how do we connect these changes to a temperature scale? Now, remember that temperature can be defined as a measure of the warmth or coldness of an object or a substance with reference to some standardized numerical measures or scales. Three common scales are the Fahrenheit scale, which is used mainly in the United States, the Celsius scale, which is used everywhere in the world, and Kelvin, which is used in the physical sciences. The Kelvin scale is also known as the absolute temperature scale. Here's a chart of the common temperature scales, Kelvin, Celsius, and Fahrenheit, and it compares values for reference and some example temperatures. So for example, on the Celsius scale, we've calibrated 0 to be the freezing point of water and 100 to be the boiling point. In the Kelvin scale, this is 273 and 373 respectively. And as you'll notice, there's the same number of degrees or units between freezing and boiling in both of these scales. The Fahrenheit scale has freezing at 32 degrees and boiling at 212 degrees. We won't go into this, but there's a historical reason for this result. In addition, we can see some reference temperatures where, for example, carbon dioxide solidifies, oxygen liquefies, and of course, absolute zero. On the Kelvin scale, absolute zero is 0, whereas with the Celsius scale, it's negative 273, and on Fahrenheit scale, it's negative 460. Here are the conversion relations between the different scales. Let's look first at Celsius to Fahrenheit and back. The temperature in Fahrenheit is given by 1.8 times the temperature in Celsius plus 32. A simple manipulation of this expression would give us that the temperature in Celsius is the temperature in Fahrenheit minus 32 divided by 1.8. The relationship between Celsius and Kelvin scales is very, very simple. The temperature in Kelvin is the temperature in Celsius plus 273.16. And again, rearranging, we can get the temperature in Celsius is equal to the temperature in Kelvin minus 273.16.